person that everybody knows him, of course. I would like to say only 2 words. First of all, it's a great pleasure and nice of such conferences that you can acquaint us with the people whom you never met or meet in other places. So I met Rob now almost 10 years ago, but I knew his papers, and and after this period we more or less communicate, and because it's necessary to say some words about his abilities, one of his abilities, which is very rare for mathematician, was one term the mayor of Amherst. This period Amherst flourished and so, and the second thing, which is famous sentence, belongs to Hugo Steingaus, that if 2 persons make the same thing, mathematicians do it better. So I guess Rob supports this more. So with great pleasure I introduce Rob and we listen his interesting talk.
Well, I mean, Misha, that was a rather novel introduction, and I really appreciate it. I know a couple people in the room who've known me for a long time and have been collaborators had other views of my term as mayor, or 1/5 of the mayor. We have a 5-member junta that runs the town, and the only reason we did well, it was between 2005 and 2008. It was just before the big crisis hit, so I think it was just dumb luck. Anyway, I also want to thank obviously Misha and Keith in particular for inviting me here for the semester. And in trying to decide what to talk about, I offered Keith 3 topics. And because of the theme of the month, which is more surfaces than knots and fields and chirality, he wisely chose this one. And I'm afraid because this is a topic I've worked on for a long time with many collaborators, including one who's here from South Africa, Jesse Ratskin, who's here and come up, that it's a bit retrospective. So it's not all new stuff, and some of this stuff still has to get done, but it's been a long time coming. So it looks back for a few years. So anyway, I haven't used this before. Let's see how this works. So that's the title. And this is obviously not soap bubbles, but it's a fountain over just west of here at Cavendish. And if you, let's see, the pointer part is this part. Where is the pointer button?
The other side, no?
In the back?
Yeah, at the back.
I don't actually see it.
Try the laptop.
There's 2. Whoops. No, that's not what I want. Oh well, I'll learn how to do this eventually, someday. Enter full screen.
Use the little cursor on the screen.
Well, I can't. I don't seem to be able to use the pointer. So. But anyway, so the thing to notice is over here there are these connected bubbles, or in this case, these are
the pointer
there.
Yeah.
Oh, okay. Just use the physical one. Yeah. So
At least.
that always works. Right. So it's obviously, I mean, I think the ones to look at, there are obviously some things that are approximately spherical, but these bubbles connected by necks, or these droplets connected by necks, and then here, in fact, closer to the fountain. So which way was the fountain flowing? You can probably tell from where the connected, most of these are disconnected as single droplets. Then over here we see these 1, 2, 3, 4, 5 perhaps that are connected together. And in fact, as the fountain spouted its water, it was roughly a cylindrical cross-section coming out, but lots and lots of turbulence. So the problem that I'm looking at is governed not by the energy of the fluid inside, but the really surface tension and the pressure inside. So the problem I'm looking at really should be thought of as a problem where I have 2 dominant terms of the energy, and one of them is surface tension, comes from surface tension, and the other one comes from the pressure inside. And unfortunately, in this little experiment with big fluid drops, there are lots of other kinetic energy terms from the fluid moving around inside. So unfortunately, I couldn't get an inkjet printer to show very small scale droplets where the surface tension dominates and the pressure dominates and there's little fluid motion. But if you've ever seen very microscopic fluid jets, those actually are much better models for this problem than even soap bubbles or these big droplets are. So the problem I'm looking at really is the surface tension, the energy associated to it is essentially the area. Okay, so it's the area. And the pressure energy essentially is related to the volume of the fluid that the surface encloses. And in the case of an incompressible fluid like water, the problem, typically that's a parametric problem or a problem where I'm looking at a stationary surface, I'm trying to minimize or find critical points of area. Area times surface tension would be the surface energy with a volume constraint. That leads to a Lagrange multiplier problem. If it's a compressible fluid, then like in a soap bubble, then it's typical to think of the pressure the pressure turns out to be proportional to the mean curvature. So the mean curvature of a surface, if I have some surface, at each point there's a normal, and there are so I can look at planes that are contain the normal, and they cut the surface in curves, and there are two principal directions where those curvatures of those curves reach their extreme values, and their curvatures, the principal curvatures K1 and K2, they're the reciprocals of the best fitting circle, and so those are the principal curvatures. The mean curvature is just the average of all these curvatures, or the average of the principal curvatures. So this is the mean curvature, and typically the energy that we'll look at looks like that. So that's sort of treating it like a soap bubble rather than where I get to fix H to start with. And in fact, in the case of a soap bubble where I have a non-trivial volume constraint, so soap film, there'd be no volume constraint, and there I could take the Lagrange multiplier to be 0 or the mean curvature to be 0. Here I'm going to have something non-zero, and I usually normalize so that the mean curvature is 1. So the Euler-Lagrange equation for basically making the first variation of this thing equal to 0. And if I take that, let me just take that away, then that's this equation right here. Okay, so that's the subject I'm going to look at. So let me give you a few sort of in the spirit of, let's see how this works. So here's some examples of, of more complicated surfaces of constant mean curvature. So think of a column of fluid coming out, and then maybe they scatter. So this is something I couldn't visualize out at the Cavendish, and then they see scattering like this. Okay, for the fluid. And here's another example like this. So these are some typical examples of very unstable constant mean curvature surfaces. So there's a in the case of the fluid coming out, there's of course of that jet. Starts out as a cylinder, and the cylinder, as well as I guess the round sphere of radius 1, the cylinder of radius 1/2, sphere of radius 1, both will have 0 in the case the cylinder is 1. The sphere, all the principal curvatures are 1. So out of the fountain, what it tends to do is it breaks up into these undulating kind of pieces, and I'll show a video of that in a second. And then eventually it breaks into, the undulations get stronger, and eventually it breaks into these droplets. That's what we saw. And so the so-called Rayleigh instability of the column of fluid. I want to think of this as a kind of a scattering. There's the same picture. Again, not so much of the droplets, but I want you to imagine loops or strings traveling along these droplets, and they interact in some strange way. So in some sense,
Just check them out.
oh, is it not coming through? Sure. I turn it off?
It turned itself off.
Okay.
Sorry, I just need to go and get another one.
Can you hear me in the back, even if they can't hear me out in radio land? Okay. Right. So again, this is a kind of an idealized universe of strings scattering along the bubbles themselves. And since we're here at the Newton Institute, I thought I'd summarize what's known about these surfaces with sort of Newton laws for soap bubble scattering. And I'm going to make a couple assumptions. One is that I'm dealing with just a finite number of incoming and outgoing strings. So I don't really care. This time isn't really this problem. This is an equilibrium problem rather than a dynamics problem in some sense. And so I can think of these as incoming, these as outgoing, but I can also think of three of them as incoming, that one is outgoing, or all of them outgoing. And since I'll think of things sort of going out to infinity, maybe I'll just psychologically think of them as outgoing in each case. And in this case, I've got 4 scatterers, and however they scatter is there. So this number of scatterers is finite. In mathematical terms, this is the number of ends of the bubble, the number of ways to go to infinity. And also the number of loops in this diagram for the scattering is going to be some finite number. That's the genus of the bubble. So let me just go back again to this picture. The genus, whoops, I don't know why it does that. The genus here, there are no loops, is 0. The number k is 4 of ends. And here it looks as if there's a loop, but in fact, if you look very carefully, this is not a physical bubble anymore. It's a sort of mathematical idealization where the bubble passes through itself in a ghostly manner. So there's really, this is again a case where there's 4 ends, 4 ways to go to infinity, but there's no loop there. So that loop, that apparent loop isn't really a loop. It's just the bubble is just passing through itself in a ghostly fashion. Okay, so these are both the same topological type of bubbles. And in fact, you know, how the loop propagates along the bubble, I'm not interested in either. So I'm not really interested in the how the bubble's parametrized. So that's sort of the physical system that we're talking about. It's a kind of idealized system. And then this is a theorem which I call physicsy fact, and it's the analog of Newton's first law, which is that if I have no interactions, then if I simply have a 2-ended bubble, so there's an incoming and outgoing, if you like, or just there's just two ways of going to infinity, then in fact the surface is exactly one of these unduloids. And I want to show a quick video of that, so I'm going to escape this. Let's see. Now, there's all this stuff that came up when we went into video mode, so I think I'm going to get rid of this. I don't know how to do that. Get that out of the way. Get that out of the way. So this is the family of unduloids. Can you see that? Okay, so there's a, actually this is a single unduloid. These are actually made by a former student of mine almost 10 years ago at Gang. And if you want to see better pictures and more interesting videos that take longer to watch and to load, please go there. But so these are periodic surfaces of revolution with constant mean curvature. And they come in a family. And as I said, the family interpolates between the chain of spheres and the cylinder. Let's see if I can do that. Yeah. And I'll just run that. Now, if I stayed with embedded surfaces, I would stop there at the chain of spheres, but actually the family continues into an interesting class of immersed surfaces, the so-called Delaunay nodoids. And those don't figure so much in our theory, but it's good to keep in mind that there are these other kinds of surfaces. Okay, so that's the Delaunay unduloid family. Whoops. How do I get back to the, whoops. There we go.
What's the evolution rule when you say they evolve? Right? I mean, you have constant mean curvature. That's a steady state condition. Then you say there's an evolution rule. What's the evolution rule?
Well, the evolution rule for the string is really just that the mean curvature is constant. So it's, if you like, if I think of it of a curve on one of these surfaces, there's an initial value problem, which is it's a second order initial value problem. There's the position of it, and there's also its, if you like, its first order behavior. And so it's only a locally well posed problem, the evolution rule. If you think of this as an evolving system, because it's an elliptic. It's an elliptic system. Mean curvature 1 is essentially, looks like leading terms like Laplacian.
I think the question is if it is evolving dynamically.
Oh, dynamically.
Yeah, what's the dynamic evolution rule?
So by the way, the answer is that's not included in the problem that I'm looking at. So for me, I'm just changing various parameters
I see, so
that
it's a
govern.
parameterized problem.
And the parameters are, and that's actually the next thing on here is the what are these parameters? So in the case of the unduloids, you can think of them as a mathematical problem. There's a way of actually generating these. This goes back, in fact, to Delaunay himself in the middle of the 19th century. The cylinder, of course, I can think of as being generated by the rotation around an axis of a straight line. That axis is gotten by, in a curious way, I roll a circle and I follow the focus of the circle, the center of the circle. Of course, that just rolls down a straight line. These unduloids are obtained by rolling an ellipse and following the focus of the ellipse. That gives not a straight line, but something called an undulary, analog of a catenary, if you like. And then I rotate that around the axis. So all I'm doing in this problem, is a geometry problem, is I'm changing the eccentricity of the ellipse. Now, what actually happened in the physical problem, the Rayleigh instability is, if you will, it's driven by a second order effect. So the equilibrium condition is mean curvature equals constant. The second order effect is governed by an elliptic equation that looks like this. I take the Laplacian on the surface plus the sum of the squares. This will come back in a minute. And I look at solutions to this equation. So this is the so-called Jacobi equation on the surface. And on a cylinder, this is a constant. It's, I don't know, 4, I guess. And so the solutions, if I separate variables, are basically sinusoidal as well as various things. So the perturbation, this, if you like, is the second variation of that energy, this left-hand side here, okay? And so to get an idea of the second order effect, I see perturbations like this, so-called U is a so-called Jacobi field on the surface. And on the cylinder, what you see is these sinusoidal undulations. So if you think of it as a second order perturbation, that's what's driving it. But I'm not going to get into that too much. So okay, so this family is parametrized, if you like, the one we went through. It's parametrized, if you will, by the eccentricity of the ellipse that rolls this out, or if you like, by the so-called neck size. So there's an N is this neck size, which is the length of the shortest curve on that unduloid. So the neck size, this N, takes values. Well, the chain of spheres doesn't really count as a two-ended surface, but you can think of that as a limiting case of the neck size is 0, and if I get up to the cylinder, I have pi for the neck size. So there's an interval of these things. Okay. And physically, at least in equilibrium, there's a force vector. This is Newton's second law, if you like, a force vector associated with each unduloid. And if I think of the axis unit vector as giving me the direction, then the force is, well, for small n, it's actually proportional to the neck size itself. So it's actually, there's a little nonlinear correction. In fact, this term here is if you like, the surface tension term. And this other term with the quadratic term in n is the pressure term that compensates that. So this is really the force you would experience if you made a rope out of a fluid droplet or a soap bubble, and you carefully measured the force in that droplet. Okay. And so then the hard result, actually, the theorem essentially is in fact that any of the ends of these CMC surfaces are asymptotic to some unduloid. So there's some neck size and some direction in space, in fact, some axis in space, That each end is asymptotic to, and if I calculate the force vectors of the ends, then they have to balance. So, for example, let me go out of the. So, in the case of a two-ended surface, in fact, I could have a priori. I could have an unduloid going off one way, some other unduloid going off another way, maybe even in different directions. But the force balancing tells me, no, they have to be the same neck size unduloid, because otherwise the magnitude of the force, and they have to be oppositely oriented. And a little more work shows, in fact, that in fact they have to actually, the axes have to line up, and the phases have to line up. Okay, there's no way to sort of have a phase shift in the unduloid.
Rob, does that second one tell you that you can just glom on chains of spheres or cylinders wherever you want because there's no force?
Well, spheres have no force, and in principle you could attach them anywhere, but that doesn't give you an honest CMC surface. It gives you a disconnected CMC surface. And then one of the big industries, and I'll say just a tiny bit about that, is to decide what happens near such a chain of spheres if I want to perturb it to a very necky, very small neck-sized unduloid. And when you do that, of course, you introduce a tiny little force along that chain of spheres, and then the rest of the surface has to bend a little bit to compensate. So that's a big industry, and Jesse has worked a lot on that in particular. Okay, so that's sort of the physics-y picture of this. And more mathematically, I'm taking a surface of finite topology. I don't care about the parameterization. And I'm looking at surfaces that are embedded, basically. But they're embedded in a slightly weaker sense. Remember that very first picture that we had here? This one over here. So the surface itself is not embedded. This one is. This one has, it's the boundary of some embedded three-dimensional object. This is the boundary of an immersed three-dimensional object. All right, so it's you can't quite get the immersion of the three-dimensional object to be one-to-one, but we can still immerse the object. So there's the differential is non-singular, and this type of thing is a so-called Alexandrov immersed surface. So it's not quite embedded, but there's an interior three-dimensional object that immerses, and that's enough to sort of keep track of sort of inside of the surface, even though there's no inside. So this is the class of surface we look at. And then just to summarize this theorem, the mathsy fact, that's the Newton laws, is two-ended surfaces are these unduloids.
So sigma's a compact surface? What's sigma?
Yeah, sigma bar would be a compact surface. Sigma is the surface with punctures, so it has holes. Those go off to infinity. That's what proper means. And it might have some topology. Okay, so there might be some genus, but I'm just assuming finite topology. So the way of going off to infinity really looks annular topologically. And it turns out it's one of these Delaunay unduloids.
It's worth mentioning that in the embedded category, there are no interesting compact examples.
Yes, actually, that is, thank you. So in fact, for zero ends, Alexandrov showed about 60 years ago now that there only is the round sphere. That's why we only see the round sphere in some sense among actual soap bubbles in nature. And in fact, Bill Meeks, right around the time we were doing this work and Motivated, that showed that one-ended surfaces, ones that have just one way going off, are impossible. And you can understand that in terms of force balancing, because one end, in fact, would have to go off like an unduloid. So this is a posteriori. And there'd be a force on that one end, and so the surface would just sort of pull away to infinity if there were a one-ended surface. So the only interesting case begins with two or more ends. And in fact, so there's the asymptotics, and then we can think of this force balancing in a somewhat more intrinsic way. If I take a curve along a surface, then so let me cut the surface here. If I take some curve, then there's a pair of quantities that are worth looking at. One is the so-called conormal. So this is a vector field which is tangent to the surface but normal to the curve I'm looking at. So this is this conormal. And then I could take the normal to a cap. So that's what K is. So gamma is this curve here. K is a cap. Nu is the normal to that cap. And this just gives the pressure force. This gives the surface tension force. And that has to balance. And it turns out that just depends on the homology of the curves. It doesn't really depend on which curve I pick, just the homology class.
Does there exist a surface that would connect very close spheres of fixed radius in the limits of the separation going to zero?
Yeah, so that's these Delaunay unduloids. But the problem is they have to go all the way to
No, I
infinity.
mean, the spheres. You take two spheres,
Two spheres.
bring them very, very close.
Right. So
Can you connect them?
you can, but not with constant mean curvature, because this Alexandrov theorem says they would actually glom together and come to equilibrium and
A
stuff.
naive question. These unduloids, each one goes to infinity.
They go to infinity, both
In what
sides.
sense you talk about ends? They're really spokes.
Yes, an end means a way of going to infinity. So it doesn't. An end is not something that ends. An end is something that never ends. There's no end at the end. The end goes all the way to infinity.
Yeah.
Yeah.
It's a puzzling terminology.
Well, it's unfortunately one that the topologists came up with about 100 years ago, and we're stuck with it. So, right, the ways of going off to infinity. So those first examples had 4 ends, and you're supposed to imagine them going off the screen forever. All right. So in fact, this was also a nice motivating thing. Again, almost 25 years ago. Once we have, well, with 2 ends, we only have these unduloids. With 3 ends, it turns out we can have surfaces of any topological type. And again, let me just show you a family that I think is an interesting family that illustrates. So I'm going to just get rid of these Delaunay surfaces. I think this is what yeah. So this actually, to some extent, addresses Conrad's question. Let me pull this back. Let me just move through this family. So there is a bunch of spheres touching, and if I move a little bit in the family, I can put in these little tiny necks. They're a little bit like catenoids. And the thing is, there are now forces introduced when I do that, and those forces have to be held somewhere, and they're held by infinity. So infinity applies pulling forces on this. So if you didn't actually go to infinity, you need to introduce boundaries, some kind of a wall where you attach the soap bubble to the wall. And as you move through the family, these necks get bigger and bigger.
In order to keep this
In equilibrium.
shape, you would have to hold it.
Have to hold it out near infinity.
Yeah.
Yes.
It might be useful to think of it as periodic boundary conditions.
Well, I was going to say, does it complicate or simplify if you connect the ends in pairs?
Well, if you connected them in
Heterogeneous.
if you connected them in pairs in 3 space, then again you end up with a compact surface, and that would eventually collapse under some kind of thing. So that's a bit. Now, for the experts in the audience, there are a couple who've worked in the 3 sphere. Connecting them that way does lead to interesting things in the 3 sphere, and I might make a comment about that, but given the time that I'm spending on this, I may never get to those kind of more technical remarks. But this family here, maybe I'll just run the family. Let me start it back at the beginning, because somehow it's not quite sure how to run this thing. Yeah, there we go. So here's a family going through all the possible neck sizes of 3-ended surfaces of genus 0. And what's interesting is you reach a place somewhere about there where the neck sizes get maximal, and then they start getting small again. And just about now you leave the embedded class, well, not now, and you get into this Alexandrov immersed class so there's some slight numerical mess up there, so the mean curvature doesn't really look like it's staying the same. But what I think is most notable about this is that you never get out to the cylindrical neck size. So one of the questions that actually motivated us for many years was, could you have a surface that had 3 cylindrical ends? Okay, we know that the cylinder is one with 2 cylindrical ends, but could you have a surface that looked like this? And these go off to infinity, so does that exist? And say at g to 0. And this example, the so-called equilateral example, where all the neck sizes are equal, doesn't seem to have that. So that's a.
So what's the parameter you're changing?
The parameter I'm changing here is the neck size. So this is so the neck sizes that we see here vary in the family. So I'm sort of not answering your question by answering it this way. They vary like this. Now this parameter I haven't told you what it is yet. To tell you that one, I'll have to tell you a little more of the theory. But the neck size is changing. It's going up through a maximal neck size, and then it reaches some maximum, and then it descends again.
So is that symmetric in time, in whatever we are seeing?
Yeah.
You're going back on the same path.
It's not.
After the neck
It's
size
not the
is
same
maximum.
path. Let's look at that again. This is worth understanding because this is. If I don't convey anything else, it's that there's some kind of interesting phase in the problem. This is the first example of that. So here, in the middle, there was a bubble. Now I get to this sort of intermediate, can't tell if it's a bubble or a neck, and now the middle becomes necky. Necky.
Yeah.
So Rob, then is there some duality between the maximal and minimal neck?
Well, no, I mean, the necks are. So the neck size, there's a pair. There's a pair. So there's a pair of these, of the same neck size. There's one with if you like a bubble in the middle, and there's one with a neck. So there's a bubble and a neck, and I'll make a comment on that in a minute. So let me show you one other phenomenon.
Well, is that changing the parameter that for the foci of the ellipse where they pass through
Yeah,
each
so
other?
the neck size is essentially the eccentricity, or it's related to the eccentricity of the ellipse.
Do this, then you would
Yeah. So for the unduloids,
maximum to minimum.
right, the unduloids, it's just the neck size that determines the shape. Obviously, where the axis is and what the phase is along the axis is what determines the surface in space. Here, there's more than just the neck size. There's this parameter that Conrad is asking about that I'm keeping in my pocket for another minute. All right, so let me show you one other example that I think is even more interesting, and I'll just let you look at it for a minute. So now it's, again, a 3-ended surface. The neck size on this end I'm keeping fixed. The next, let's do that again.
This one actually is a loop in the parameter space.
This is a loop, and thank you. Yeah, I've got a stuffed up ear, so I can barely hear out of this side. If I turn this way, I can hear you. But notice, let me go through it slowly. So notice how the neck size changes in these other 2 ends over to the left. Whoops. So they get much bigger. They get to that equilateral position pretty much, and then they shrink back down to something smaller. Now, because of trigonometry, of course, the force balancing is correct throughout the process. But although it's a loop in parameter space, notice what seems to be happening. There's a bubble being generated there. So it's a loop, but if you keep track of the phase, if I mark, let's say, this loop here.
You're just blowing with fancy straws, and, horizontal one.
Yeah, so look where this neck goes. It starts there, it ends up going from, it just moved over one. So it's a loop, but it's a loop with some kind of hole in it over here. So I think that's an interesting thing to keep in mind. All right, let me go back to the beamer part of the talk. I think that's all I'm going to do for the going outside of this. And given how much time I'm spending on this, I probably will have to recalibrate. So yeah, so we have these examples, and those are some 3-ended examples. So it turns out they come in a family. Capelleus didn't construct the whole family. He constructed families near the ones that Jason asked about, which was where the neck sizes are all very small. And the idea was basically to take bubbles and glue them together by tiny necks and keep track of the forces. What you need is a configuration that balances out your infinity to start with and balances everywhere else. So now let's see how I can do it. So the questions really come, so these next size bounds, this why you can't get all the way out to next size pi for the triples, for the three-ended surfaces. So can you do something like that? Or do you see something that comes to some intermediate range? Why are they there? And these pairs, so there's the bubble in the middle and the necky bubble. So this is sometimes called an outie. If you know a little bit about surfaces, any these surfaces with three ends have an umbilic point, a place where the two principal curvatures are equal. So an umbilic point could either be an outie or an innie, and those are the two types one sees. And what is it that accounts for that pair of different things? And then I think this bubble generation, we saw that sort of phase shift as we go around the loop. What accounts for that? And so there's some moduli space theory that I want to look at briefly with you guys that tries to keep track of this sort of phase phenomenon as well as the neck phenomenon. So there's the neck size as well as phase phenomenon that's interesting in the problem. Okay, so let me just quickly go through this. So there's a space of all surfaces with mean curvature 1, and I'm assuming embedded, that have the topology that we're interested in, say genus G and KNs. And it turns out that on the remember, each end is asymptotic to an unduloid, and it turns out that the space of unduloids is a little more complicated than. So I only have these little boards to use, right? The space of unduloids is a little bit more complicated than just the neck size, because there is the axis, which it is a surface of revolution about, and there's also a phase angle, right? So the space of unduloids with a given axis, I can think of as a disk with a cylinder at the very center of the disk, okay? Because cylinder, it's invariant under translation, and so when I don't see any phase information there. Nearby the cylinder, all the unduloids with a slight neck size, there's really a one-parameter family of them. So these are the unduloids with a given axis. And out at the edge, really, I shouldn't include the boundary. This is the chain of spheres. So what I see is a two-disk here, two-dimensional disk. And if I take all the unduloids, right, all the unduloids, let me call that U, the set of all unduloids. Well, this is a disk across the space of axes themselves, oriented axes. That's space of lines. Okay, so this is the space of lines. The space of lines is really a four-dimensional space. It's the tangent bundle of the two-sphere, if you like. So this is the space of unduloids here, and this is the space of lines, oriented lines in 3 space. And so this is a six-dimensional space, and it turns out that it carries a natural symplectic form. Okay, I mean, there are various ways of defining it. One way actually uses the Jacobi equation, but this turns out to be a symplectic 6-manifold. And if I take the k-fold product of this, if I take U to the k, it just carries the symplectic, so say a symplectic form carries the symplectic form, just the k-fold product or some of those things. And it turns out that this space of unduloids, it's going to be this space of CMC surfaces of a given genus, it sits, I can sort of just map it into the space of k-fold copies of space of unduloids just by taking, for each end, I take its unduloid asymptote. And when I map it in that way, it turns out to be an isotropic surface. So this is an isotropic manifold. The symplectic form vanishes on that. That's another way of really talking about force balancing. So really force balancing in some sense captures that. And there's a notion of non-degeneracy in this theory, and I'm not going to say much about it in view of the time, but it turns out that non-degeneracy is essentially saying that remember I wrote down that operator, I'll use this space here, right, the so-called Jacobi operator, so k1 squared plus k2 squared times u. If I look at solutions of this equation, then these are like infinitesimal variations through constant mean curvature surfaces. These govern how these are tangent vectors, if you like, through constant mean curvature to the space of constant mean curvature surfaces, or to this moduli space. And it turns out that this condition of non-degeneracy is like the Morse theoretic condition of non-degeneracy at a critical point. Okay, and in fact, what it means for this problem is that that if I have a variation that decays near infinity, it has to be identically zero. Okay, so if u decays, so if u is square integrable, say, on the surface, okay, and satisfies this, then that implies u has to be zero. That's what non-degeneracy means. So that condition written there, if I have a solution to that equation that's square integrable, it decays near infinity, has to be zero. That's what non-degeneracy means. Physically, it says that somehow the asymptotic behavior, the boundary conditions of infinity, completely determine the surface, and that's what this third part of the theorem says, is that essentially you get a manifold that's completely determined by the kn's. So actually, why do you get 3k for the dimension? Well, you can think about it in terms of the force vectors, if you like. Okay, so each n has a force vector, an element of R3, and those three n's, those kn's, can be 3k parameter family. So,
Sorry for a silly question, but what is U?
u is a function on the surface. So I think yeah, it's a function on the surface. So remember, in the case of the cylinder, right? The cylinder, this became Laplacian plus 4, and u is basically just it's a normal perturbation of the surface. So the perturbation,
Linear stability.
it's the linear stability. It's the second derivative, if you like, of the functional or the.
How would we define that for that three-prong funny straws?
Right.
You
Right.
have a normal vector, and
Right.
you just look at normal graphs over the surface.
Yeah, the problem is the Laplacian is harder to define on complicated surfaces. Right? On a cylinder, you know what to do. You separate variables. In general, it's hard to write this down explicitly in coordinates on a manifold, and it's the Laplace-Beltrami operator. But u is basically the normal component of a variation. Okay. So maybe I'll say a word about non-degeneracy, because I'm really so this non-degeneracy problem, I think, is actually one of the hardest problems to understand. And it turns out there's an analog to these soap bubbles in R3 with minimal surfaces, soap films in the 3-sphere, and if you could prove an analog of that, so trying to prove that this non-degeneracy condition holds for constant mean curvature surfaces is still, I think, the main open problem in the subject. A little bit would be known. We could get some interesting corollaries if we could do this for the analog in the 3-sphere. In particular, we'd have a finiteness theorem for minimal surface in the 3-sphere. And since got a couple visitors here, I thought I'd mention that 60-some years ago, Hupf, and later really Almgren, I guess was the first one to write it
So
down.
this is saying there's only finitely many which satisfy the appropriate non-degeneracy condition?
Yeah, so for a minimal surface in the
Minimal
3-sphere,
surfaces.
yeah, in the 3-sphere, that if I had non-degeneracy, then the conclusion would be up to just rigid motions, there'd only be a finite number of surfaces of a given topological type. And so it's been known for a long time that the round sphere, the analog of the Alexandrov theorem, has been known, or Hupf theorem, in fact, for genus 0. And for genus 1, it was just this year that Simon Brengel showed again by showing there's only one example of an embedded minimal surface. So this problem, is far from being solved in in either the three-sphere or for soap bubbles, for minimal surfaces in three-sphere or for soap bubbles. About 5 years ago, Jesse and I and Nick Korovar were able to prove that for most coplanar surfaces, now coplanar I'll come to in a minute, that they're non-degenerate. And a couple years later with Carson Gross-Brockman and John Sullivan, we were able to complete that argument. So coplanar surfaces are examples of CMC surfaces that come up pretty naturally. These three-ended surfaces are coplanar. And I'll say a little bit about those now. Obviously, a surface that has two ends, we said had to, the ends, because of force balancing, had to go off in opposite directions. And so, in fact, that surface ends up having to lie in a solid cylinder. A three-ended surface, because of force balancing, the ends all have to, well, if the forces have to balance, it means the ends have to go off in directions that lie in a solid slab. And that's what coplanar means. Okay, so a surface is coplanar if it has finite topology. In fact, I'll make the genus 0 just for the argument. And I want the surface to be contained in a slab around a plane. Okay, and it said this is automatic when k is 3 or less, or k is 2 or 3. So all the three-ended examples were coplanar. It's an extra condition once you have 4 or more ends. And it turns out that coplanar surfaces are more than just lying in a slab. They actually have some symmetry. So this is an analog of this Alexandrov theorem for non-compact surfaces. A coplanar surface has to be reflection symmetric. So the top and bottom halves of the surface that you get by applying the symmetry actually turn out to be graphs. Graphs in the sense of that there's a function over a domain in the plane of symmetry. So the top half is a graph over that domain, and the bottom half is its mirror image. And that means that in the genus 0 case, the graph, the surface is a graph over a disk. The disk goes off to infinity, so it's a disk. It's a sort of a, if you like, it's a disk. If I just look at the actual thing drawn on the board, I see a disk on the board that goes off to infinity, and the surface comes up on one side towards you, and the other side it goes back into the board, and that's what every coplanar surface looks like. It's a union of two graphs, okay, like this. And again, there's a moduli space at these. It's a submoduli space at the full space of surfaces. I'm taking genus 0, so it's in N0K, and I'll just call these MK. And it turns out that these form, so earlier we saw that they were, all of them formed a 3K minus 6 manifold under the assumption of non-degeneracy. Okay? Now it turns out, as I said, these we know are non-degenerate. It's a long story of why they're, but before we knew that, we were able to prove that these form also a manifold, and the dimension is basically K less than that. And why do we have this dimension count here? Well, let's just understand why these come in these families. So each end has an x size, and each end has a direction which I can move out in. So there's the 2K. And force balancing in the plane means I get to subtract 2. Forces don't really see the rotations, so the rotations give me another 1. So there's the 2K minus 3. Okay. Now, that's not really how we do it. Okay, and this gets into the question of geometric phase. It turns out that there's a way of actually completely parametrizing this space, and it turns out that we need to use a kind of a synthetic construction to associate the space of constant mean curvatures with a space of metrics on a, well, really on the disk over which I represent the top half, say, of the surface. Okay, so let me just take a minute. I have only about 10 minutes left to describe what that is. So what I want to associate to each constant mean curvature surface is a metric, which has locally the geometry of the unit sphere. Okay, and we call these K-point metrics. A K-point metric is a metric that again, locally looks like the sphere, but it's a metric on the disk. So it's a little hard to imagine what that might be. Maybe a good example is what I'll call a two-point metric. So let me jump down to this one. So imagine in complex analysis, you take the exponential map. So that takes the complex numbers, that's the plane, it's topologically a disk, to the plane minus a point, right? Which you can think of as the Riemann sphere minus 0 and infinity, minus 2 points. Okay, so that exponential map wraps the plane around the sphere infinitely many times, and it actually misses 2 points. Okay, I can take the spherical metric on the sphere and I can bring it back to the plane. So what I see is if you like, I see the plane wrapping around the sphere, and every strip on the plane here's the sphere. Take, say, 0 and infinity. If you like, I'll just make a cut there. That cut there corresponds to basically a strip in the plane. Say a strip from, say, well, in fact, if I think of this as the exponential map, I should probably draw the strip horizontally, say from the level 0 to level 2 pi I, that level here. And the exponential map is wrapping this strip once around the sphere. But what I do is I endow this strip with a spherical metric. Okay, so you can think of it in other ways. Think of the sphere as being, I'll just slit it, I'll cut it along here, and I'll take another copy of it. Well, another copy of it is another strip, and I'll glue that copy on. Okay? Another slit. And I'll do that again, and again, and again, and again. All right? So that's the spherical metric that has, that corresponds to k equals 2. And this metric is interesting as a metric space. If I go out, if I go around this direction, so if you like, if I go in this direction or this direction, those paths have infinite length. So I'm not gluing, by the way, I'm not gluing there. I'm gluing this edge, say this dotted edge here, and then I proceed. If I go up to the point at infinity or down to the point at 0, that's a finite distance path. And so in order to get a complete metric, I've got to add a couple of points. I've got to add the points at 0 and infinity. And so a k-point metric is a metric that has locally the geometry of the sphere. It's not a complete metric, but when I complete it, I can do it with exactly k points. Okay, so a 2-point metric turns out to be exactly something that comes from something like the developing map. In fact, all the 2-point metrics correspond to doing this construction that I just did, except I don't take the 2 points to be antipodal. I take the 2 points to be separated by some distance, n. Okay, n turns out to be the next size. N is some distance. There are 2 points. It's in the interval 0 to pi. Okay, and then I just do this construction. I slit here, and I take another copy of it, another copy of it, another copy of it. It turns out that the unduloids correspond exactly to these 2-point metrics. And the next size of the unduloid corresponds to the distance between the 2 points. Okay? So that's the correspondence that we make here. All right, that's about all I can tell you on that, given the time I have. Now, the fact that this space of k-point metrics has dimension 2k minus 3 is sort of, should be kind of clear, these spherical metrics, right? Because a metric turns out to be locally determined by these completion points. Okay, the completion points, what I do is I can develop the k-point metric. It's a spherical metric. I develop it into the sphere, and those completion points go to k points on the sphere. K points on the sphere locally determine what the metric is, and so I get a 2k parameter family of images of those completion points. But I can, of course, rotate the sphere, and when I rotate the sphere, that's the ambiguity in specifying that metric. That gives me the 2k minus 3-dimensional family of k-point metrics. Turns out that's the space of CMC surfaces. This is the theorem. There's a diffeomorphism between these two spaces. The constant mean curvature surfaces that are coplanar and these k-point metrics. And to go from one to the other involves actually a fairly elaborate procedure. We take this upper half of the coplanar k-anguloid. It's topologically a disk. It turns out there's a minimal surface in the 3-sphere that's intrinsically isometric to it. And the boundary curves of the top half, there are these 3 planar curves, or k-planar curves in general for a coplanar surface. Those turn out to go to Hupf circles in the 3-sphere. And then when we Hupf project, what we get is we get a map then from this minimal surface, it's disk-like, to the 2-sphere. These curves here on the boundary go to the k points on the 2-sphere, and the metric on the 2-sphere, after Hupf, we pull it back by Hupf projection, gives me a spherical metric on the top of the CMC surface. It's a very indirect construction for this. Okay, and it turns out that well, this is a little. Let me just jump through this. We could write down explicit formulas for how to do this. I think I won't do that, but it turns out there's an interesting thing that Jesse and Nick and I discovered was without going to the minimal surface of the 3-sphere, you can think of this map to the 2-sphere kinematically. As I say, it turns out that there's a very kinematic or synthetic way of constructing the map to the 2-sphere. If you take any curve along a constant mean curvature 1 surface, remember I said there's a conormal to the curve, so there's a vector field along the curve that's tangent to the surface but normal to the curve. And if you take a sphere and spin it around the axis of the conormal, okay? So if I start at some point, at some base point on the surface, okay, and then I want to go to some other point, I want to define a map from the surface to the sphere. Turns out it's this map that I described with the minimal surface. But there's another way to think about it is I take some base point, on the sphere, okay? I'm going to tell you how to get a map from any other point on the surface to the sphere. I'm going to do it by spinning the sphere. That'll tell me where this other point goes. So base point on the surface, base point, let's say the North Pole on the sphere. I take that point to the North Pole. Now, I spin the sphere along an axis that is the conormal to the curve. So it's a tangent vector to the surface, normal to the curve. And I spin it at a rate. I've got to tell you the rate at which I spin it. I spin it at exactly double the rate at which I'm moving along the curve, so double the speed. It turns out that defines a path-independent map from the surface to the sphere, and that's another way to think of this map. So it turns out you can promote it to a map to SO3 or even the 3-sphere, and it's another way of synthetically constructing the minimal surface.
So the remarkable thing is that this thing you've described is a flat connection if and only if your surface is mean curvature 1.
It characterizes the mean curvature 1. So it's a kind of a connection picture for a principal bundle picture. Okay. And so just examples is here. So this correspondence between minimal surfaces in the 3-sphere and CMC surfaces in terms of examples. The equator of the sphere corresponds to just the round sphere in R3. The Clifford torus in S3, at least locally, corresponds to the cylinder. And the Delaunay surfaces correspond to sort of necky versions of a Clifford torus, but they're not embedded. Okay. Okay. So let me skip some of this stuff because I'm now essentially out of time, and come to the main results that I wanted to explain. So it turns out that the space of all these surfaces is, in the case of 3 ends, it turns out it's a three ball. And let me show you how that works, at least because I think it illustrates this problem about the neck sizes as well. So remember, for 2 ends, I was able to identify these So this is supposed to be identified with the space D3 of spherical metric with 3 completion points. Well, spherical metric with 3 completion points, okay, so this is the picture of the spherical metric. See, the 3 completion points, when they develop to a triple of points on the sphere. And just as we did for the two-ended case where I took the distances, I could take the distances of 3 points. Let me call those N1, N2, and N3. And in the same way that the distances for 2 points correspond to the Delaunay neck sizes, it turns out that these distances correspond to the asymptotic Delaunay neck sizes in the three-ended case. So the spherical metric kind of looks like I take a little spherical triangle synthetically, and now let me just show how to make it so that's not a complete metric yet. To make it a complete metric, what I need to do is here's a boundary where it's not complete. If I take a sphere and I slit it along a slit that has exactly the same neck size, then again, I can attach, say, this side to this, and now I get a metric that's, again, on a disk. The disk is this triangle together with this other disk attached. All right, so if you remember the picture that was on one of the earlier screens. There's a triangle. Here's the abstract disk. Here's this triangle I have here, and then this split sphere corresponds to an extra region like that. Okay, and I do that again and again. I keep repeating. So I touch infinitely many of these off on this direction. And that sort of fills in that area on the disk. And I do the same thing here, and the same thing here, and that gives me all these metrics. So it turns out that the space of triples of points on the sphere, on the 2-sphere, is really just a 3-ball. All right, it's a 3-ball you can see rather explicitly, and in fact, it sort of answers the question we had about these neck sizes, because you see what's the biggest triple of neck size you can have? Well, the biggest triple you can have is when the triple happens to lie along the equator. 3 points along the equator. The neck size is then N1, N2, and N3. For example, if I make them all equal, they would correspond to exactly a third of the equator, which is obviously less than the pi that I got for the cylinder. And that's what we saw in that example there. So the family that we saw, the parameter that Conrad asked about, in some senses, if I start with a very necky example here with a very small triangle, expand that triangle until it becomes a hemisphere with the 3 vertices along the equator, and then continue down to get a very bubbly surface in the middle, I'm going from neck size 0 to this maximal neck size 2 pi over 3 in the collateral case, and then back down to the 0. So it turns out it's this family, not the neck size, but this family of metrics, which in this case is given by the triangles that do this.
So in other words, time is going down in your picture. It's going down that vertical
right. In that animation, the time parameter, the parameter that was over there, was the latitude parameter.
What makes it asymmetric? Why is a small triangle at the top different from a small triangle at the bottom?
Well, because remember the triangle, if you like, is an oriented triangle. It's really an ordered triple of points. And so the small triangle at the top that you see, it bounds a disk on this side. When I get to the bottom, it's bounding a disk that wraps all the way around the sphere, almost all the way around the sphere. So I'm being signaled to stop here, and I will, if you allow me just 1 second. So it turns out that in general, we were able to show that this space of metrics, surprisingly, is also a disk, or a higher dimensional disk, which is a little bit unusual because in the case of more than 3 ends, where we don't necessarily have coplanar surfaces, there are non-trivial loops in the moduli space if I leave the coplanar category. So I could sort of twist one pair of ends with respect to another pair of ends. But in the coplanar case, it turns out that there's a way to understand these using basically a slightly weaker construction than spherical metrics. It's the space of projective structures, and that's probably subject for a different seminar. So I think I'll stop there. So it turns out that space is naturally an affine space, and so we end up with contractible space. So thanks for letting me go over a minute or two.
Rob more or less expand his time. Only one question from the persons who not asked during the talk.
Well, that's pretty restrictive.
I do it in question.
Yes.
Sorry. Initial energy, two terms, surface tension, area, and pressure, volume.
Right.
So only one length scale ratio on both of them. But all picture contains at least two scales, size of the neck and size of the bubble. Where it comes?
So actually, that was one of the questions I was going to ask you guys. But in fact, it's not an independent scale. The mean curvature I'm fixing to be 1. So that's why I get rid of that. And then it turns out that in fact the size of the bubble is not that different from the size of the neck. So remember the construction, right?
Yeah.
It's this and this. So it's the size of the mean curvature basically tells me which family of ellipses I'm in. That's the neck size, that's the bubble size. So it really is only one length. But I sort of faked it by picking my mean curvature to be 1. That's the mathematical trick that I did. Yeah.
The last question.
Any thoughts about curvature equals 0
So
or minus 1?
curvature equals, so mean curvature 1 corresponds to these spherical metrics in this way. Minimal surfaces, interestingly enough, correspond by a similar thing to certain flat metrics, so curvature 0 metrics synthetically. I didn't get into the last part of this, and don't tempt me, but projective structures actually, the way to understand them is actually to use a combination of curvature -1 and curvature 0 metrics. So there's a whole theory that goes back to probably way before Thurston, but Thurston made a big impact on this in the last 20 or 30 years, which is you study projective structures by putting metrics on surfaces that have hyperbolic parts, curvature -1, and flat parts. And the flat part tells you sort of how much you bend the surface. And it turns out that's what completely captures the projective structures. So I'm not really answering your question very well, but that's...
So because Rob is here, so we'll
You can
get
ask me
this
now.
after.
Yeah, thanks.